Alright, so the problem that we are going to solve today is number 22.38 in the textbook, and this again just deals with Coulomb's law. So here we have four identical charged particles that all have Q is equal to plus 10 microcoulombs located on the corners of the rectangle. And we are asked to calculate both the magnitude and direction of the total electric force exerted on the charge of the lower left corner by the other three charges. So we're going to call the one on the lower left corner number 1. And then here we have number 2, number 3 up here, and number 4 down there. So the first thing we're going to do is calculate the magnitude and the equation for that. So F21 is going to be the force exerted from 2 onto number 1. So what is the force number 1 feels because of number 2, right? And that is going to be equal to KE Q2 Q1 over R squared. We just care about the magnitude, right? So it's magnitude of Q1, magnitude of Q2. Now we know that Q2 and Q1 have the same charge, Q, and R is just the distance separating the two, which is this one here. And we know that that is W, it's giving to us. So here is going to be KE Q squared over W squared. And if we were to plug in the numbers for that, we get 40 newtons. Now for F31 here, that's what is the force exerted by charge number 3 on charge number 1. And they are spaced by this distance here away. So they're on the diagonal. They both have the same charge Q, so it's going to be the same thing, Q squared. And then here it's going to be the square root of L squared plus W squared. But because it's R squared, that's squared. So that gives us KE Q squared over L squared plus W squared. We plug in numbers for this one and we get a value of 2.35 newtons. Now F41 is what is the force by 4 onto 1. So what is the force that 1 feels because the 4, and we see that they are separated by a distance L away. So that's going to be KE Q squared again divided by L squared, and we plug in numbers for that and we get 2.50 newtons. Alright, so that answered A, which is the magnitude. But for part B, we want to know the direction. First thing we can look at is, well, we know that they're all positive charges, so we know the force is going to be repulsive. So for instance, F41, the force by 4 on 1 here, is going to repel 1 in this direction, negative x hat, right? It's going this way. Now F2 on 1, the force by 2 on charge 1, is going to repel force number 1 down here in the negative y hat direction. As for 3, it's going to repel it off the diagonal. So there's going to be a negative x component and a negative y component. Because we are going to be dividing F31 into its components, we'll define this angle here to be theta. And then we can say the following. We can say that the F total, so the net force in the x direction, is going to be equal to negative F41, right? Because 41 is going in the negative direction, in the x negative direction, and then negative F31 cosine of theta. And why do I say that? Because if this is my theta, this is going to be F31 sine theta, because it's in the opposite side, and this one is going to be the cos. So this is the cos side, and this is the sine side, right? Now in F total y direction, so in the y direction, we are going to have negative F21, so that's pointing it down here, negative F31 sine of theta. Now what is theta? Well, if I just look here, we know that theta is equal to tan minus 1 W over L. The reason why I use the tangent is because we're explicitly given L and we're given W, and I don't really want to do any extra steps. I plug that in, that is about 14 degrees. I plug in all of my numbers, so the values I obtained down here, right, for the magnitude, and I get negative 4.78 newtons in the x hat direction. So this is in x hat. and I get negative 40.57 newtons in the y-hat direction. I can report the answer as such, so F net, the vector, is going to be negative 4.78 newtons I-hat and negative 40.57 newtons j-hat. And this is one way to report it, right? You're saying this is how much is in the I and this is how much is in the j. And if we look here, we see that there's a lot more in the negative y direction than there is in the negative x direction. And that actually makes a lot of sense because we see here that this configuration, so charges 1 and charges 2 are much closer together than charges 1 and charges 4. And because the force is dependent, right? It's like the distance apart they are, it does matter quite a lot. So this charge feels a lot more repulsion due to number 2 than it does to number 4. So it makes sense that it's pushed a lot more down here, which will give it a net force somewhere in this area down here. Another way we can report this number is by giving a magnitude for the F total and then saying what's its angle with respect to this x-axis, right? So that here is phi, where phi goes from here all the way to here. One way that I would calculate this is by saying, well, what is phi prime? So what is the angle here, this little angle, and then if I add 180 degrees, I get the whole rotation over here. So if I do that, what I see is, well, first I'm going to calculate the magnitude of F net by taking the square root of negative 4.78 newtons squared plus negative 40.57 newtons squared, take the square root of that, and that is going to give me 40.8 newtons, right? So that's just the magnitude. And then I want to know what phi prime is, so I'm going to say tan of phi prime is equal to Fy divided by Fx. And the reason why I do that is because, again, I want this angle, and I already know what these components, the Fy and the Fx components, are here. So I'm it's pretty easy for me then to be able to figure out what the angle is here if I know what this is and I know what this is. So I plug in my numbers here and I get negative 40.5 newtons divided by negative 4.78 newtons, and that will give me a value of phi prime is equal to 83.268 degrees. So what I'm saying again here is that my angle here is equal to 83.268. So in reality, if I were to draw this properly, F net is pointing way down here. So we see that the effects from this charge is a lot more than the effects from these two charges because it's pushing it a lot further down here than it otherwise would have. Now, like I said, phi is just going to be 180 degrees plus 83.268 degrees. And that is going to be 263-ish degrees. Okay, so that's the answer here.